part 2 of section 11, we're going to get to Cramer's rule. So we're going to be focusing on just applying Cramer's rule to linear systems of two variables. And the statement here says using determinants to solve a linear system is called Cramer's rule. Theorem 11.1 is going to give us the information we need for Cramer's rule. So it starts off saying the linear system, and it provides us with a linear system. That would be this right here. And there's a lot of letters and variables going on here, so I want to be sure to clarify what this system represents. So this system is really no different than any of the other two variable systems we've seen. For example, if I say 2x minus 3y equals 12, negative 7x plus 4y equals negative 2. I'm just making up a system. This is exactly what we're talking about here. So the a1, b1, c1 would be analogous to the 2, the negative 3, and the 12 that we have in that first equation. So the a1, b1, c1 are the coefficients and the constant that go with the first equation. That's why we use a subscript of 1. Then, if I look at the second equation, I have an a2, b2, and c2, and then those will be associated with the coefficients that go with the second equation. So all of your a's and b's are meant to represent a real number that will actually be a part of the system. So Cramer's rule just generalizes the idea that every single linear system with two variables will look something like this. And it also goes on to claim that there's a way to calculate the solution. The solution is going to be the ratio of some determinants. So x is going to be the ratio of determinant of dx divided by the determinant of d, and y will be a similar ratio where it's the determinant of dy divided by the determinant of d. And I know that you know how to work with ratios because you dealt with ratios back when we talked about slope, delta y over delta x. So really the big question is, where does the matrices d, dx, and dy come from? Because after you've come up with those equations, or those matrices rather, you know how to calculate the determinant. That's what we did in the previous examples. So where does the d, dx, dy come from? Well, it tells us that here as well. It says where d is equal to the following matrix, and it says a1, b1, a2, b2. So this matrix D right here, this is what I like to call the coefficient matrix, because it is focusing specifically on the coefficients from the system. So let me wipe the system clean if I can. There we go. And A1 and B1 are coming from the first equation, and A2 and B2 are coming from the second equation. So the first row of matrix D is always associated with that first equation. The second row will always be associated with the second equation. But there's also another connection here that is also really important, which is the columns. So the column A1, A2 is associated with the A1, A2 that we have, of course, here in the system. Those are all coefficients for an x. X from the first equation, x from the second equation. I call this the x column. The B1, B2 are both coefficients coming from the y's. So I call this the y column. And that's going to become really important as we look at creating these next two matrices, because up until now, every problem I've given you dealing with matrices, I have provided you with the matrix, and then you have performed the operation or the stated the order or whatever it was about the matrix. Now you're having to create the matrices yourself. So we know how to create matrix D. Matrix DX is going to look almost identical to matrix D, except you are not going to include the X column. So what you'll notice, if you look at the Y column for matrix D, the Y column is copied down over here in DX. Those are identical. But I'm going to be taking C1, C2, and I'm going to be inputting those where the X column would normally be. So DX has the X column removed and has it replaced with C1, C2. DY is created in the same fashion. DY is going to actually include the X column, which is the X column from matrix D, but I'm going to exclude the Y column. That's why we call it DY. And what I will replace it with is I will take that C1, C2, and I will have it go where the omitted column was. So this is how we will create the three matrices, D, DX, and DY. Then we will need to perform the determinant calculation times 3, because there's 3 matrices, and then put them in the correct ratio to solve for X and Y. We will not be doing any addition. As far as the addition elimination is concerned, we won't be doing a substitution method. If you do this correctly, it's just going to spit out the answer for you. And all it's going to take is a little organization and a little arithmetic, and that's it. One last thing though to mention is what's going on over here at the end. It says the determinant of D is not allowed to be 0. That becomes significant once you start looking at the ratio for X and Y a little more closely. The ratio for X and Y both have a division by the determinant of D. So if the determinant of D ends up calculating to be 0, that means that you'll be having a division by 0. And you can't have a division by 0 in the ratio. So therefore, you're not getting an appropriate X or Y calculation. You're going to get something that's undefined. What that means is that Cramer's rule is not going to give you the answer that you want precisely enough. What it does mean is that you will end up not having a intersecting lines case. You would have either a parallel lines or a same lines case. If that occurs, then you need to go back and actually investigate the equations more closely to determine if your equations are parallel or if your equations are exactly the same. Because if you get a determinant for D of being 0, I can go ahead and tell you it means you're not going to have that one solution intersecting lines case.